Good morning, everyone. Welcome back to our standpoint logic course. So yesterday we finished with starting this section on expressive standpoint description logics. So after having seen standpoint EL and having noticed that adding standpoint modalities to the description logic EL preserves its computational complexity, that is reasoning in deterministic polynomial time, we have also had to acknowledge that certain things we cannot express in EL. Foremost, negation and disjunction, which are very useful things if you want to describe more complex relationships between concepts in your domain. And so we moved up to a more expressive description logic called SHIQ. So allowing, in addition to all of these things, also role hierarchies, inverse roles, and qualified number restrictions. We have seen the syntax, right? So we can do everything we did in EL, but also negation, disjunction, universal restriction, and number restrictions. And additionally, we have these standpoint modalities within complex concepts, meaning we are in the monodic fragment. Right? So monodic, meaning if we were to translate this into standpoint first order logic, we would allow one free variable to be in the scope of a modality. Right? Then we have seen that knowledge bases are transformed into a certain normal form simply for technical reasons to be able to treat them more easily. Right? So there are still many case distinctions to look at, but with normalizing we can decrease the number. And then we have stopped here where I said for standpoint SHIQ, we also have a small model property, albeit it is of a slightly different nature than the one we had for sentential first order standpoint logic. Right? So there, the thing was we only had to look at all diamond subformulas or unsatisfied boxes and make sure we keep witnesses for those in our model. The rest we could throw away. Right? So that was the idea. Here we are in a monodic fragment and we really have to take care of single individuals. So we cannot simply throw away everything, so we have to keep some more. And Sebastian and Lucia put this into this definition. And also, as you can see here, the model is still small, but not small in the sense of being linear in the size of the formula, as we had it for the sentential first order standpoint logic. In this case, it might be polynomial. So it might be larger. So it's still of a manageable size, so something that we would still call small, justifiably so, but it's not linear. So they introduced this notion of having a tidy model. Right? So this model is a description logic standpoint structure. Right? So we have our description logic domain, our set of individuals, which is shared across the precisifications in pi. We have our usual function assigning precisifications to standpoint names and the function assigning description logic interpretations to precisifications. And then they say such a model for a knowledge base in normal form is tidy if the following conditions hold. Right? And these conditions say the precisifications contain exactly. Right? So not more, but also not less. Right? So everything that has to be witnessed must be witnessed. So that's the at least. And then the tidiness intuitively expresses that you don't have any spurious additional precisifications that you don't really need for witnessing something. Right? So the only things that are in there witness something that does have to be witnessed. Right? And these things that have to be witnessed are, first of all, the standpoint extensions must be non-empty. Right? So for each standpoint name in our vocabulary, we must have at least one precisification. For every diamond subterm that occurs somewhere in our knowledge base, we must have two witnesses. And for every diamond subterm and individual name, we must have one additional witness precisification. So that's the idea, right? So with this, with these, you basically witness the named instances that could be instances of this diamond SC concept. And then with these two, you witness the anonymous, so the unnamed instances, right? Because it could always be the case that your knowledge base requires certain things to be diamond S's, so to sometimes or conceivably belong to C, while they are not necessarily being an individual name for these things. And what this means is, well, the number of such subterms is bounded by the size of the knowledge base. Right? The number of standpoint names is bounded also by the size of the knowledge base, because you cannot have more standpoint names occurring in the knowledge base than you have than the size of the knowledge base. Right? And so overall, the number of precisifications that you end up with is polynomial in the size of the knowledge base, right? And that makes it small, and that is useful because if we then want to check satisfiability, it suffices to look for tidy models. So that's the underlying idea, right? Because in general, models could be infinitely large. However, if we know that we can restrict to tidy models, we have to look for much fewer things, and that sometimes makes it easier. And the actual small model property result then says if we have a satisfiable knowledge base in standpoint SHIQ, then it also has a tidy model, right? And the proof is similar to the one that Tim showed you. If we have a satisfiable one, so if we have a model of a knowledge base, then we can essentially prune it and throw away the stuff that's not required for tidiness. That's the idea. And the key property that can be used in this language is that the standpoint logic, the description logic SHIQ has a very nice property, namely that if we take two models of a plain SHIQ knowledge base that are disjoint, we can take their union and we still have a model. And that is quite useful because then the idea that these two had was that we can, in a sense, create copies of our domain, so infinitely many, right? But that's not a problem. So we will then have an infinite domain, but the size of the domain is not an issue, right? For tidiness, the only interesting thing is the number of precisifications, right? So that's what matters to us. And then the idea is that these two precisifications will witness all of these diamond S memberships. Then we also introduce precisifications for individual names, witnessing the diamond S memberships for the named individuals. And then there's some additional technical work to be done, making sure that you put the correct copies in role relationships. Right? So you start from an original model that satisfies everything in the knowledge base, and there are certain things in role relationships. And for all of these things, you create infinitely many copies, and you have to make sure that you put the correct copies in relation with each other. And this is not fully trivial, but also nothing that I want to go into here. So you can have a look at the respective paper. So what this gives us is we can, without having a model beforehand, actually translate standpoint SHIQ into plain SHIQ, right? Using this result on the small model property. And the idea for this is to essentially compile away the standpoint modalities into the vocabulary, into the description logic vocabulary by creating copies, right? So the idea is you look at the knowledge base and you know basically, if this knowledge base is satisfiable, then it will have a tidy model. Right? And that gives you, by simply looking at the syntax, gives you an upper bound on the number of precisifications you will maximally need in a tidy model. Right? And those we call pi k. And we know if there is no model with these pi k many precisifications, then it's unsatisfiable. Right? So it suffices to just search models of this kind. Right? And then what we do is we compile away the standpoint modalities, making sure it works like the semantics say, right? By compiling the precisifications into the vocabulary. And the blow-up is only polynomial because we only have polynomially many such precisifications. And also the sharpening statements can be expressed using GCIs. And then what this gives us is, starting from a standpoint SHIQ knowledge base, this translation will produce a plain SHIQ knowledge base, so a description logic knowledge base without standpoint modalities. The translation can be computed in polynomial time, right? Because we can easily obtain the precisifications that we need, and then we only have to create as many copies as we have precisifications. And that's the important bit about this result, this translation preserves satisfiability. Right? So the original knowledge base is satisfiable if and only if its translation is satisfiable. So we essentially keep the semantics, modulo then having a different vocabulary, but the idea is that from any model of our translation, we can reconstruct a model of the original knowledge base. And so this essentially allows us to compile away these standpoint modalities and use existing reasoning systems for SHIQ, for example, so more or less out of the box. Right. So to summarize, in SHIQ, we also allowed concept-level standpoint modalities. So still, we had a monodic fragment here. We translate this into a normal form. For normal form knowledge bases, we have this small model property, this notion of a tidy model, saying that I have only those witnesses that I really need for sub-concepts of the form diamond as C, and those are only polynomially many. Right? And this property then gives us, via some additional work, a polynomial time translation from standpoint SHIQ to plain SHIQ. And therefore, since the blow-up is only polynomial, we achieve the same complexity. Right? So plain SHIQ is X-time complete, and this gives us only a polynomial blow-up, so we still have X-time completeness for standpoint SHIQ. And this, therefore, is again one of the cases where we could add standpoint modalities computationally for free. Right? So one of the nicer cases. And the practical consequence is that we don't have to implement a new system. Right? We can just use existing description logic reasons that can cover SHIQ. And the only thing we have to implement is this translation. Questions on this? None so far. Okay, then you might ask whether this is the end, right? Whether this is the most expressive we can do. And also Sebastian and Lucia asked that question. And they managed to even go beyond this SHIQ. Right? So they had to use different techniques because in the case of SHIQ, they heavily made use of this disjoint model union property. Right? So taking two disjoint models, their union will again be a model. For more general languages, this is not necessarily the case. So they had to use other techniques. So one of the more expressive description logics in that case is this SROIQ BS, right? So here, so along with SHIQ, so the S and the I and the Q are just like in SHIQ. Here with R, you then have role inclusion axioms. The O stands for nominals, which typically also create computational issues. And the BS is for safe Boolean roles. So that's another quirk, another technical detail where you have to make a tiny adjustment and a tiny restriction to keep decidability. So those are, again, so SROIQ and also SHIQ BS are more expressive description logics, right? So for SHIQ, you can even see in the name that it extends SHIQ. And they underpin important web ontology language description logic profiles. But it can be shown that they can be expressed, or at least the relevant reasoning problems can be expressed in C2, the two-variable fragment of first-order logic with counting quantifiers. So if you attended the invited talk on Tuesday on the expressive power of graph neural networks by Flores Hertz, you might remember that he also talked about these CK logics, right? So first-order logics with counting quantifiers, only that sometimes he allowed more than two variables, but here we restrict to two variables and counting quantifiers. Right? And so what Lucia and Sebastian observed here is that even for this very general language, so restricting to the monodic fragment, you still have a polytime translation into plain C2. Right? And because this translation is polynomial time, you again keep the complexity. And because these expressive description logics, so the two underpinning these web ontology languages, can be cast as fragments of C2, we can also express them within this framework. Right? And this is an important result because essentially the syntax of this C2 is much easier and much nicer to describe than the explicit syntax of these expressive and complex description logics. Right? So for SROIQ or for SHIQ, for example, you have S, so you have ALC plus transitive roles, and then you have role hierarchies, you have nominals. So you would have a great number of case distinctions to look at. In C2, the syntax is built by only looking at the usual first-order logic plus these counting quantifiers. You only have to make sure that in all of your subformulas, you only ever use two variables. Right? But this is a slightly smaller technical issue than having to look at all of these cases in these complex description logics. Right? So this is a really nice result because you have a nice and small language, but it is still computationally expressive enough to cover these more complex cases. But in order to prove something about these expressive languages, you don't have to look at them explicitly. You treat them implicitly via looking at C2. And so this is a really nice and useful result. Now, again, the question is, can we move beyond this? Right? And as I mentioned before, it is not always possible. I mean, it is most of the time it is not straightforward, and sometimes it's plain impossible to add standpoint modalities to expressive logics, right? So it doesn't always come for free. I just happen to have shown you several cases where it works. And typically, adding nominals is one of the culprits, as I said. Right? So it's even the case that for the description logic EL, where we could show that we can keep polynomial reasoning, there also nominals cause trouble. Right? But also here, for SHIQ, we have seen that plain SHIQ has X time complexity if we add standpoint modalities to a monodic fragment, then we keep exp time. The same for C2 and its related description logics. But even for ALC, only extended by nominals, right, already gives expressiveness or gives complexity of exp time. In the plain case, adding standpoint modalities gives you a jump in complexity. So, right, so at least we have a hardness result to that end. And the idea, or one of the reasons, is that nominals must be interpreted identically across precisifications. Right? Because we said we have the rigid constant assumption or the rigid individual interpolation assumption. So we say individual names are interpreted identically across all precisifications. And since nominals are simply individual names used in parts of classes or in place of classes, then this carries over to nominals. Right? And if you then combine this with things such as functional roles or inverse roles, this does not allow you to define a syntax on the level of description logics that, when translated back into first-order logic, keeps you within the monodic fragment. Right? So that's the problem. So for these simpler logics, we could define the syntax like that. Right? So we could simply say, so where is it? We could simply say we define complex concept descriptions in this way, where we allow standpoint modalities on the level of concepts, right? And this works. And the important thing is that if you translate these description logics back into first-order logic, then you are still in the monodic fragment. However, for these, as soon as you have nominals and other stuff, then by translating this back into first-order logic, you leave the monodic fragment, and then decidability goes away. Right? So this is one of the underlying ideas or underlying issues of adding nominals, right? And also part of the answer to the question whether we might be able to add more constructors, more expressiveness to the results we already have. Right. Okay, so that's everything on standpoint description logics. Do you have any questions? No. Okay, then let's move on. So one additional thing I wanted to show are non-monotonic standpoint logics. Right? So that's something that a student of mine and I have been doing. And the idea there is to not only allow standpointifying monotonic based logics like description logics or classical logics, but also adding standpoint to non-monotonic languages. Right? So what does that mean? Well, the logics we have seen so far, so in particular the classical propositional standpoint logic, but also first order and description logics, all of those are monotonic, meaning logical entailment in these languages is monotonic. That is, if you add something to your knowledge base, then any logical conclusion you could draw before still remains valid, right? So adding more prerequisites only leads to more conclusions, but never to less conclusions. However, in practice, people from different communities or people taking different standpoints might reason differently and might also reason non-monotonically. So they might apply different defaults. They make might make different assumptions, right, when using vocabulary in a specific way. And in particular, in practice, we face the issue of not always having complete knowledge about all the details in our domain in a certain application. Right? And typically, dealing with incomplete knowledge is dealt with by making some useful default assumptions in a way that we can withdraw them later on should it turn out that these assumptions have been wrong. Right? So the cornerstone, or one of the important things about non-monotonic logics, is that we can make such assumptions, but in a way that doesn't lead to inconsistency if we later learn that some of the assumptions have been wrong. Right? So we want to have a specific technical way of withdrawing some of these assumptions, and thereby also withdrawing conclusions that are invalidated by not having this assumption anymore. So our goal in this sub-project was to combine the multiple viewpoints that we have in standpoint logic with the non-monotonic reasoning capabilities of existing logics, where we can make assumptions and also retract them if it later turns out to have been unjustified. And the approach that we chose was that we used a specific modal logic called S4F, and I will introduce it in a minute, as the base logic for doing non-monotonic reasoning within each standpoint. And what we obtain from this is a logic that generalizes both standpoint logic, so the propositional standpoint logic that this course started with, and this modal logic S4F. And we will also see, and I will also show you why we chose this specific logic. Right? So, because it's not very well known, but it is very useful because it encompasses and it covers many other existing non-monotonic logics. Right? So just like C2 covers these very expressive description logics, S4F covers quite a number of existing non-monotonic logics. So that's what S4F looks like. So the name derives from extending the modal logic S4 with this axiom schema F. Right? So S4 means you have the K axiom, you have T and 4 if these names say anything to you, otherwise just ignore it. And additionally, you have this F axiom, which looks complicated, and so it's more accessible to look at the logic from a model theoretic perspective, because if we look at how the structures look like, it is easier to grasp what the logic does. So the syntax is fairly easy. It's a unimodal propositional logic. So you have atoms from some propositional vocabulary. You have negation and conjunction. Therefore, you have the whole Boolean language. Right? And you have this modality K. And you can read it, and typically it is read in the context of unimodal S4F as it is known. Right? So phi is known by some not further identified or unnamed agent. So that's the syntax. And in the semantics, we again have structures. And these structures, so these S4F structures, are special forms of Kripke structures. So you have worlds and you have an accessibility relation. However, because the accessibility relation is always more or less the same, the structures are a bit restricted. So we only have two sets of worlds. So they must be disjoint. And essentially, the idea is that we have some outer worlds and we have inner worlds. Right? So the idea is that we have these inner worlds, W, and then around them we have some, or maybe that's not a good way to draw it. So around them we have these outer worlds. Right? And so what happens, or what the intention is is, so we have this psi that assigns a propositional valuation to each world, just like in a cryptic structure. And then the idea is that our outer worlds can see the inner worlds, right? So any outer world can see not only every outer world, but also every inner world. The inner worlds can see each other, but the inner worlds cannot see the outer worlds, right? So those from outside, they can look in, but those from inside cannot look to the outside. So that's the idea. And this gives you, and this is small or somewhat small change, gives you useful additional modeling leeway, so to speak. And this property of outside worlds can look in, but inside worlds cannot look out, is expressed in this definition of satisfaction in this logic, right? So the satisfaction of the remaining connectives are just standard, right? Just like in propositional logic. The only interesting case is that of the modality, and there, in a certain world W, it is the case that the structure at W satisfies that phi is known, if and only if, and that depends on whether the world where we are is an outer world or is an inner world. Right? So if it's an outer world, that means we are here, then in order for phi to be known, phi must be true in all worlds, right? Because the outer world can see all outer worlds and all inner worlds. So phi must be true in all the worlds that this world can see, so to speak. If this is an inner world, it suffices that the formula is true in all inner worlds, right? Because the inner worlds can only see all other inner worlds, but they cannot look outside. So that's the idea. And the point is, and we will see this later on, that these S4F structures are used as potential counterexamples in the process of minimization. So all of these worlds are possible in the overall structure, and they determine what is known in the overall structure. The inner worlds are globally known to be possible from anywhere. The outer worlds affect what is known overall, but their presence is not necessarily known everywhere in the structure, right? Because in an inner world, you're not aware that this outer world exists. And if we were to phrase this as an ordinary cryptic structure, we would obtain the set of worlds that is simply the disjoint union of inner and outer worlds, and we would have the reachability relation saying, well, outer worlds can see outer worlds can see inner worlds, and inner worlds can only see inner worlds. Right? So that's the reachability relation we would obtain. Useful properties of S4F that also hold are that we have a small model property. Right? So satisfiable theories have models of linear size, and the idea here is the same. So this basically uses standard ideas that Joe Halpern and Shoham used already in the 80s for standard modal logics. And Mirek Troszczynski and Viktor Marek showed this in the 90s for S4F. Right? So the idea is always you look at unsatisfied boxed formulas. In this case, it's K formulas, and you keep the witnesses of those. And since there are only linearly many K subformulas, you only have to keep linearly many witnesses, and that gives you the small model property. Satisfiability is NP complete, so that means adding this K modality fortunately does not give you any additional complexity in comparison to standard propositional logic. Right? So you can say more, you can express what is known and not known, but you don't have to pay in terms of computational complexity. Right? And by reducing entailment to satisfiability, you get co-NP containment for entailment. Now, this semantics, the syntax and semantics alone does not yet give us a non-monotonic logic. right? So for non-monotonicity, we need some more. Namely, we need to restrict the set of models from which we do our actual reasoning, right? Our actual entailment. And for this, the idea is we want to restrict attention to models where what is known is minimal, so-called minimal models, right? So we start from an S4F structure where there are no outer worlds, right? So you basically only have these inner worlds, and they give you an S5 structure, right? And S5 then refers to the case that the reachability relation amongst these worlds in your structure is an equivalence relation, basically. So we start from this, from such a structure without outer worlds, and we want to determine whether it is a minimal model, right? And minimal refers to what is known as minimal, or in other words, whether the set of worlds considered to be possible in this structure is maximal, right? So if we really have incorporated all of the worlds that actually satisfy everything that goes on in our knowledge base. So we say an S4F structure, and this now might contain outer worlds. We say it's strictly preferred over this S5 structure if looking at the evaluations of the outer worlds is not contained in the evaluations of the inner worlds. In other words, there is some outer world here that has a valuation that does not occur anywhere in this structure, right? So this relates to this: have we really included any world that is possible and that satisfies our knowledge base, right? And we say that this is strictly preferred if it contains such an additional world, right? But of course, I mean, if we have a structure that does not contain every valuation, we always find the strictly preferred one. Of course, we should also consider whether this preferred structure is also a model of our knowledge base, right? And so for this, we have this notion of a minimal model. So a minimal model is always an S5 structure, so no outer worlds at this point. It must be a model of the theory, right? And it must be the case that there is no S4F model of the theory that is strictly preferred. And the idea there is that we, in this S5 structure, really have taken all of the possible worlds, right? So there's nothing that we could potentially add to our structure. It is, however, important that we do this check against an S4F structure, right? We could also say, well, an S5 structure is minimal if we don't find another S5 structure with strictly more worlds, right? That would give us a different logic. So in this case, it's really important that we do the check, the minimality check, against candidates that can be more generally S4F structures, right? And they must have the same set of inner worlds. So this is really one of the important points, and that goes back to work by Gregory Schwartz and Mirek Truszczynski in the late 80s and early 90s that discovered that you can build very useful and very nice knowledge representation logics using this minimal model characterization. And then Truszczynski and Marek and Schwartz showed that this logic has computational properties. So it's slightly more complex than standard propositional logic, but that is not an issue because many other non-monotonic logics are also more complex. And typically, the increase in complexity is one level of the polynomial hierarchy, which is exactly that we see here, right? So the sigma P2 says you can make one guess, and then you can use a polynomial number of oracle calls using an oracle for problems in NP. Right? And then the reasoning problems that we are interested in are looking at whether something holds in one minimal model or in all minimal models, so-called credulous and skeptical entailment. So why is this logic interesting? So I already mentioned that Troszczynski and others observed that this logic can express other existing non-monotonic formalisms. And first and foremost, what it can express is Raymond Reiter's default logic. So that was one of the most prominent non-monotonic logics. And the idea was that you have these defaults. So those are just formulas of some base logic. In our case, it's propositional logic. The original proposition or the original proposal by Reiter was that it is first order logic. So the idea is that whenever you know that phi holds, you can consistently assume that all of these psi m hold, then you can conclude psi. And we will later on also see a concrete example where we use our standpoint non-monotonic logic to model a small example there. And so this can be expressed in S4F as follows. So we can say if you know phi and you know that you don't know that psi is false and so on for all of the psi, then you can conclude that you know psi. Right? So this is roughly the idea here. And so if you look at this, it might look complex at first, but you can also interpret this as a diamond, right? Because it's the not k not. The k is a box, right? And the not k not box not is then a diamond, right? So this says if you know phi and you know that psi1 is possible, right? Conceivable and so on, then you can conclude that you know psi. Right? The same logic can also express normal logic programs, but even the extended logic programs, which I haven't put here, but it's equally easy. So if you have a logic program rule with default negation here for some body literals, and basically it again becomes an implication in S4F, where instead of having general formulas after the k, you only have atoms after the k. But the general idea is the same, right? So if you know P1 and you know P2 and so on until knowing Pm, and you know that you don't know Pm plus 1 and so on, you know that you don't know Pm plus n, then you can conclude that you know the head of the rule, right? So that's the idea here. And then there's an even simpler, but also very popular non-monotonic formalism, so-called abstract argumentation frameworks proposed by Dung in 1995. It was known that they have a close relationship to logic programming, but also those we can cover using S4F, at least under the stable extension semantics. So here the idea is you say for all of the arguments, the argument is known unless you know that it's not known, basically, right? So by default, you can accept it unless you know it must be rejected, right? And then the second component of these AFs are so-called attacks, where a containment of a pair in this relation says that A attacks B. And here you can simply say, if you know A, so if you have accepted A, then you know not B, right? So then you must reject B. So that's the idea. And the important thing that we can see here in these translations, the translations work bit by bit, right? So you can translate a default on its own without having to look at the other defaults and having to look at the rest of the knowledge base, right? You can translate a logic program rule by rule, and you can translate an argumentation framework argument by argument and then attack by attack, right? And this is an important property because it simply means your translation is much easier to compute. You only have to walk through the knowledge base once and you have your translation. In comparison, the translations that we have seen from standpoint SHIQ, for example, to plain SHIQ, there you had to look at the whole knowledge base, compute all of the precisifications, and then use all of those precisifications, compile them into the vocabulary and so on. Right? So you need to look at everything and use this information then to compile different things. Here you can look at a single rule, and if you later extend your knowledge base by another rule, then you just translate that rule in isolation, and you get the overall translated thing. So this is a useful property, and of course, these translations are also semantically faithful, so they preserve the semantics. Of course, this is something we expect, but still, it is important to say this. So that gives us the important role of S4F, and that was our motivation to use S4F as the base logic for standpointifying it, if you want. And the idea is that to propose this S4F standpoint logic, we again start from a vocabulary containing atoms and standpoint names. We again have sharpening statements, saying that S is sharper than T. And in the syntax of our formulas, we have the same propositional logic as before, as we had for standard plain S4F. But instead of having only the K, now we have a multi-modal logic. So now we have box S for any standpoint name. We still have the universal standpoint. So we move from a unimodal S4F with a K to a multimodal S4F with these standpoint modalities. And so what we can do now is we can express defaults that we had before, right? So knowing phi, assuming that the psi hold, we can conclude psi, right? We can now not only express these defaults globally, so to speak, but we can localize defaults to certain standpoints. Right? And this is then just implemented, if you will, by replacing the case that we have in this translation of a default into S4F, into unimodal S4F, by the respective box, depending on the standpoint according to which this default holds. Right? The rest of the translation stays the same. And we will next look at one specific example relating to diagnostic defaults. Right? So this is something that we will pick up on the next slide. So here, in this running example, so this is from the medical domain, and there, for some symptoms, different communities in the medical community sometimes disagree on causes for these symptoms and on underlying reasons. So let's assume there is one community, D1, and this is simplified, but this goes back to a real problem. So in our paper, which is also on the course webpage, you can have a look at the details. So we have compressed it a bit to make it understandable, but this goes back to real problems. So we have one community that attributes certain ovulation disorders to a condition called PCOS. Another community attributes the same disorders to FHA, unless the patient is pregnant, in which case this diagnosis would not be made in the same way, right? Because then pregnancy explains it. So we have these diagnostic defaults here, and diagnostic means we reason from symptoms to underlying causes, right? And so basically this default says if we know that the patient has ovulation disorders and it's consistent to assume that they have PCOS, then we can conclude they have PCOS, right? And consistent to assume means we do not already know they don't have it. Right? Then we have this other default, so pertaining to community D2, and this is now according to the standpoint of D2, it is the case if we know the patient has ovulation disorders, and it can be consistently assumed that the patient is not pregnant and has FHA, then we can conclude the patient has FHA. Now the problematic thing here is with these two possible diagnoses that in the overall medical community, it is generally agreed upon that PCOS has to be treated with hormone therapy. FHA should not be treated with hormone therapy because it's either useless or even has detrimental effects. Right? And this we can express via, so those are not defaults, those are just plain implications of propositional logic. So we say in the overall medical standpoint, it holds that PCOS implies hormone therapy, and it also holds that FHA implies no hormone therapy. And of course, these two communities, D1 and D2, are subcommunities of the overall medical community. So we have these sharpening statements saying that D1 is a sharpening of M, right? So anything that holds in M also holds in D1, and the same for D2, right? So this is our example knowledge base, and later on we will see how our non-monotonic standpoint logic allows to do non-monotonic reasoning, right? Because the idea is that these defaults, so this is monotonic here, these two statements. However, the diagnostic defaults are things that conclude based on assumptions, right? So for example, this conclusion of FHA is based on the assumption that the patient is not pregnant. If we later have to revise some of those assumptions, then some of the conclusions might be invalidated, right? And the important question is, how does the logic technically implement such an invalidation without creating too many technical issues? And our key is to introduce standpoint logic structures and then an associated minimization definition that resembles the one for plain S4F. So an S4F standpoint structure is of this form. So you have a number of precisifications. As usual, you have this sigma function assigning a set of precisifications to each standpoint name. But additionally, you have this tau function also assigning precisifications to a standpoint name. And the idea there is that we have in plain S4F, as you might recall, we have our inner worlds and our outer worlds. And the idea is that sigma and tau assign inner and outer worlds to each standpoint name. Right? So what we had in the unimodal fashion for plain S4F, we now have in a multimodal fashion. So intuitively, each standpoint has its own S4F structure with worlds that are inner and worlds that are outer. We have to make some additional technical assumptions. So of course, the universal standpoint should cover all precisifications. So that's standard, only that we now have inner and outer precisifications. Inner worlds should never be empty, right? So this we inherit from S4F. And we have the additional requirement that inner and outer worlds should be disjoint, right? Because then we wouldn't know what to believe in such a world, right? We wouldn't know what we can see. And as usual, the gamma function then just assigns propositional valuations to precisifications, right? And as I said, the idea is each standpoint has its own S4F structure with outer world, tau of S, inner worlds, sigma of S, and evaluation function gamma. And then satisfaction of the standard connectives is standard, right? So it depends on the world where we are. The only interesting thing is how we interpret the boxes. But this is also straightforward, right? So we only combine now our multimodal standpoint logic with S4F, right? And we base the definition on the idea that for each standpoint we have an independent S4F structure. That means in order to figure out whether a box as psi holds in precisification pi, we have to check whether this precisification is an inner precisification or an outer precisification, right? Because if it's an inner precisification, then it suffices to check that the formula psi holds in all inner precisifications belonging to this standpoint that is used in the box here, right? Just like we did it in S4F. If we are in an outer precisification, then the idea is the outer precisifications can see everything. So we have to make sure that the psi holds for all precisifications, so for all inner and outer precisifications belonging to that standpoint that is being used in this box here. So essentially, we do what we did in S4F, which is do it for multiple standpoint names in parallel. And then what we can do, so this is still monotonic, right? So here we still have an ordinary multi-modal Kripke structure. In order to do non-monotonic reasoning, we again have to have a preference ordering and a notion of minimality. And the idea here is that this preference ordering implements semantical or expresses semantical commitment. So if we have different structures, so let's say we have two S4F standpoint structures, F1 and F2, then we want to be able to express that one, so let's say F2 is at least as semantically committed as F1 with respect to this standpoint S. And this is defined as follows. So they must have the exact same evaluations on the inner worlds. And on the outer worlds, it must be the case that any valuation that is assigned to some outer world in F2 must also be present somewhere in the structure F1. Can be an inner world, but can also be an outer world. Right? So the inner worlds must have the same evaluations. The outer worlds of 2 must be included in those of 1. Right? And that means intuitively that all the worlds that F2 considers possible with respect to S are already present in F1. Right? So, yeah. And then we can lift this from single standpoints to the whole set of standpoints. Right? So this semantical commitment then refers to all of the standpoint names. And for this, since we allow equality here, there's also a strict variant saying that F2 is strictly more committed if the comparison goes one way but not the other. And then we can use this preference ordering to define the notion of minimal model. And the intuition here is that we want to have models that have minimal semantic commitments. Right? So the idea is that the models commit to certain things only if they absolutely have to in order to satisfy the knowledge base. Right? That's the general idea. And again, like we had it in S4F, in plain S4F, the minimal models must be S5 structures, so there must not be outer worlds in any of the standpoints. And then we say this is a minimal model if it's a model of a theory and there is no strictly preferred S4F standpoint structure that is also a model. Right? So just like in plain unimodal S4F, we are doing this minimization with respect to S4F. But the minimal model as itself is S5, so only has a set of worlds for each standpoint. And these S5 standpoint structures are essentially like the standpoint structures of propositional standpoint logic, where we just had sets of precisifications for each standpoint. And having these minimal models, we can now define notions of entailment. So something follows credulously from a theory if and only if it is satisfied in some minimal model. It follows skeptically if it's satisfied in all minimal models. So those notions are standard in non-monotonic reasoning. They already existed in writer's default logic, so that's not something that we newly defined. We only adapted it. So now you can see in our example how this actually works in practice. So let us assume we extend the knowledge base that we had before, right? So the one with, so this one, sorry. So this one with ovulation disorders and potential diagnosis PCOS and FHA. So that was DO, so the original default theory. This we now extend by saying we have a patient that has ovulation disorders, and we express this by this box star. And then our standpoint S for F yields a unique minimal model with the following conclusions. It says, according to standpoint D1, so according to medical community D1, the patient has PCOS and needs hormone therapy, but at the same time also concludes, according to subcommunity D2, the patient has FHA and should not get hormone therapy. Right? So in this case, we can see that standpoint logic nicely allows us to keep these essentially inconsistent conclusions and incompatible conclusions separate, so we don't get an overall inconsistency because we must conclude both hormone therapy and no hormone therapy, because they are located in different standpoints, right? And this is what standpoint logic does. If they are incompatible things, it's fine as long as they are in different standpoints. Yeah, and we can then add another piece of information to our knowledge base. Right? So if we take this, so same patient, but we now learn that the patient is pregnant, right? Then basically the conclusion that this D2 has made, this D2 default, is withdrawn because we can no longer assume consistently that the patient is not pregnant. Right? So if you recall the default, it said, according to the standpoint of community D2, if the patient has ovulation disorders, and it can be consistently assumed that the patient is not pregnant. Right? And this part is then not possible anymore because we have added explicitly that the patient is pregnant. So this conclusion of FHA being universally accepted within standpoint D2 is no longer possible. So this is withdrawn. But, and this is the important bit, the other conclusion still holds. Right? So we can still learn something about the other community because simply the default making this conclusion is not affected by pregnancy whatsoever. So we can still make this conclusion. Right? So what we can see is that by having these standpoint annotated defaults, we gain something over plain default logic. Right? So we could also have expressed the same example in plain default logic without any standpoints, but then we would have obtained two extensions due to the case that one default says concludes hormone therapy, the other default concludes no hormone therapy. So we would have had two extensions, and essentially we would have had only conclusions that follow graduously. So we could have concluded these things, but only graduously because they wouldn't have occurred in the same extension. In our logic, we have one extension, the conclusions follow skeptically, and we can additionally see where these conclusions come from. Right? So you have a form of provenance. You can see why this holds. So what we have here is a combined logic that can be shown to generalize all of its constituent logics. Right? So we generalize propositional standpoint logic because S5 standpoint structures, so those without outer worlds, are essentially exactly ordinary standpoint structures that we have seen in propositional standpoint logic. But we also generalize unimodal S4F because if we just say we only have one standpoint name, then our box star essentially corresponds to the K. Right? Then we only have one modality, we have a unimodal logic, and the rest is the same. Then our standpoint structures only have this one modality, and they are exactly S4F structures. Right? And what this gives us is, well, we have standpoint S for f, and since S for f can also express default logic, for example, we now have successfully standpointified, if you will, default logic, but we have also obtained standpoint versions of answer set programming and of abstract argumentation, simply because we have dealt with this more general logic S for f. So this is the good news. Of course, the question is whether whether adding standpoint modalities adds anything to the computational complexity, right? So this is always our main interest. We are trying to find fragments where we can add standpoint modalities computationally for free, if you will. And the good news here is that also in the case of S for f and also the non-monotonic variants of S for f, adding standpoint modalities does not give you any increase in complexity. Right? So going from unimodal plain S for f to S for f standpoint logic exactly preserves complexity in this case. So, yeah, satisfiability stays in NP, right? So which is interestingly the same as for propositional logic. So you can add quite a bit to propositional logic without giving up this complexity. For minimal model existence, basically you have to guess a structure and then make sure that it really is a minimal model for which you, however, can use satisfiability. So you use the NP oracle to do to a number of satisfiability checks. Now the question is, if I say you guess a minimal model, the problem is that these models can be quite large. Right? So if you have a tautology, a propositional tautology, then the least model for this is an S5 structure containing as many worlds as there are propositional interpretations in your language. Right? Because any world satisfies the tautology. Therefore, in order to have a minimal model, you have to have a maximal number of possible worlds. And therefore, your structure has to contain all of the worlds. Right? But those are exponentially many, so I cannot simply guess the structure directly. And so the main issue in showing these complexity results is actually answering the question, how do we represent these minimal models? Right? And based on these representations, how can we show that they are minimal? So how can we show they are models, and how can we show they are minimal? Right? And for enabling this, there's thankfully a number of existing results that we can make use of. So as I already mentioned, both S for f as well as propositional standpoint logic do have the small model property. And fortunately, it turns out also if we combine this, so if we have multimodal S for f, we still have a small model property. And essentially, the proof idea is the same. We keep witnesses for all non-satisfied boxed formulas. So this is the first step. And this allows us, along with the fact that model checking can be done in P, this allows us, the small model property allows us to show satisfiability to be in NP, right? Because once again, to check satisfiability, you know the maximal size of a potential model, so it suffices to guess a model of that size. And if you cannot guess such a model, you know it's unsatisfiable. So that's the idea for satisfiability. For minimality, we have to do some more work, and this relates to the potential exponential size of these minimal models. But fortunately, there exists a characterization of minimal models that is based on the syntax of the input theory. So the idea is to look at the input theory, and in particular at all of the subformulas occurring there that are of the form box as something. So we consider, for a given theory, we consider this set, so the set of all boxed subformulas. And for these boxed subformulas, we create a partition. So basically, we put them into either of two classes. The first class says this is not known in the structure that we want to represent using this partition. The other class says this is known in our partition. And taken together, it can be shown that this defines a unique multimodal S5 structure. However, this structure is represented in a succinct way. And this is the important bit. Right? And this can also be guessed easily because we only have to look at the theory, look at all the subformulas, and then for each subformula, guess whether we put it here or there. Right? So this is easy to guess, easy to represent. And the important bit, and this takes quite a while to prove, the important bit is that you can formulate conditions on such a partition that exactly characterize whether such a partition represents a minimal model. Right? So the idea is to then only check these conditions to verify that you have guessed a minimal model by guessing your partition. And the conditions are as follows. So for every standpoint, you define a propositional theory that basically encodes the original theory, encodes what you know and what you don't know, and that also takes into account the sharpening statements that we still might have in our theory. And we require it must be satisfiable. And intuitively, this is propositional because we, in this theory, treat subformulas of this form as additional atoms. Right? So we just look at whether they are true or false, and this makes sense because on the level of an S5 structure, so something that is represented by this partition, a box formula is either true or false. Right? So either it is known everywhere or it is false somewhere. Right? But there's no need for localization, so we can just treat them as propositional atoms, and that makes things a lot easier, but still has the same computational expressiveness, if you will. Then we have to make sure that for everything that's not known, according to our partition, there's actually a world in our structure, in the structure that we represent using this partition, that witnesses that this is not known. Right? And then finally, and this is the most important bit, for everything that is guessed to be known in a certain standpoint, we have to make sure that it already follows from the original theory and what is not known. Right? So only from the theory and what we don't know, we must be able to conclude, and this is now entailment in monotonic standpoint as for f, to conclude that we actually know this psi, so that this psi actually holds. And then using a number of proofs, you can show that these conditions actually characterize the minimal models, where basically C1 and C2 characterize having a model, and C3 characterizes minimality. Right? And since this is only satisfiability in propositional logic, this is only satisfiability in propositional logic, and this is only entailment in monotonic as for f, which we also have seen to be NP complete, or co-NP complete, if you will. You can do this with overall polynomially many NP oracle calls. Right? And this gives you a decision procedure for minimal model existence. You guess a partition representing a potential model, then you do these checks. And if they succeed, you know that this partition represents a minimal model. Right? It can also be explicitly constructed, but typically we don't want to do this because it can blow up. And for reasoning from these models, it's much easier to do if you have a syntactic small representation of those. We even have an implementation of this that basically follows this guess and check approach one-to-one. Right? So we guess a partition of the box subformulas of our theory. At the same time, we guess propositional variations for witnessing the first two conditions. And this can be done, right? So out of this partition, we can construct the respective propositional theories, and then we just check whether the valuations satisfy these theories. So that's deterministic. No oracle needed here. The important bit and the most complex bit of the encoding pertains to case C3, because in C3, we have to do entailment checks in monotonic standpoint S for F. And so for this, we really have to do the model checking. And for this, we also have to use the small model property. Right? So we encode this entailment of box as psi as unsatisfiability check for this. And this we do by allowing to guess all possible small models and verifying that neither of those candidates satisfies this, and therefore it's unsatisfiable, and therefore the entailment holds. We have implemented it. It works for small examples, so you can try it out. And as a byproduct, if you disable the verification of C3, you actually also get an implementation of propositional standpoint logic. Right? So something that hasn't been done before, if I'm not mistaken, because if you only check C1 and C2 and you only use one modality, or you only use, you have no, basically you don't have outer worlds, then you don't do the minimality check and you only have ordinary standpoint logic. So multimodal, but without S4F capabilities, if you will. So what we have seen is we have seen the modal logic S4F, and it was interesting to us, and it is important in non-monotonic reasoning in general, because we can faithfully embed certain other non-monotonic logics into it. Among them, writer's default logic, but also logic programming and more generally answer set programming. So where we also have classical negation in rules, but also abstract argumentation for the stable semantics. What we have then done is we have generalized this unimodal S4F to the standpoint case, so to multimodal S4F standpoint logic. It generalizes both of the constituent logics, but can do more. We have proposed a non-monotonic semantics for this, using a preference ordering on structures that, in a sense, is based on semantic commitments. We have defined a notion of minimal models. There's also a notion of expansion. So an expansion is a syntactic or is a more syntactic theory-based characterization of minimal models, which I had, however, left out here. We have seen that the complexity does not increase, so we could basically add these standpoint modalities for free, and in particular also for default logic and for answer set programming, we could add standpoint modalities to these languages computationally for free. And we have also implemented this via disjunctive answer set programming. So we have obtained the first full-fledged non-monotonic standpoint logic. So before there were some other proposals that covered parts of non-monotonic reasoning, but here I would argue that we have something that covers a great number of existing languages already. And the nice news is, as always, that we could do this without any increase in computational cost, right? Because, as I said, this is not automatic. Typically, we have to look for certain fragments where this actually works. So this concludes the non-monotonic standpoint logic part, and incidentally also concludes the overall course. Are there any questions? So you can also ask questions to the earlier topics if something came up in the meantime. So Tim is here, and I'm sure he will be happy to take your questions as well. Yes.
I was just kind of curious if you guys have looked into how this maybe relates to some work in like formal semantics, like discourse representation theory and some other formalisms that are sort of meant for separating contexts and from a more linguistic standpoint or not. Totally fair or not, I was just curious.
I mean, I am not aware, but originally this was work done by linguists, right? So Lucia's PhD supervisor, Brendan Bennett, actually was working in formal semantics for linguistics, and this is also where this idea of having standpoints and having precisifications come from. Right? So that was what Tim was explaining in the beginning. Each one precisification is one specific way to interpret language, but there are different ways that are all equally acceptable, and we put them together in one extension for one standpoint. So that was the original idea, where we just observed that we can apply this very fruitfully to knowledge representation. I'm not aware that anyone has gone back and put this in perspective or in relation with discourse theory or other things for natural language semantics. But I think the original works of Brendan Bennett might be a good starting point to have a look whether this holds. So I would assume, so there are a number of publications where Brendan Bennett already talks about standpoints before Lucia started to work on it. So having a look there might be a good starting point. Oh yes, yeah. So the question was, how do standpoints and standpoint logic relate to other approaches in formal semantics to natural language, for example, discourse theory? Any more questions?
Maybe I just ask another question, because it seems like right now for the non-monotonic part, you don't try to make any kind of inference which might relate to other standpoints, right? So you do some kind of non-monotonic reasoning within each standpoint, but there's not a real interaction. I mean, of course, maybe this is sort of counter to the motivation of the logic because you're somehow trying to keep things a bit separate, but you might think there would be room for some kind of interaction between like some kind of global inference and then the local inference. Have you considered anything like that?
We have. So the question is, in our non-monotonic logic, there is basically no real interaction between the standpoints, right? So we can draw conclusions that pertain to one standpoint, but for example, it wouldn't be possible to conclude in D1 that according to D2 something holds, right? So intuitively we cannot really nest those, and indeed this is an issue, but also, on the other hand, it was a deliberate design decision because this effectively gives us the nice computational behavior. Right? So one of the important bits is that we require these to be disjoint. So require the sets of precisifications to be disjoint for different standpoints, and this is key in making it work. So to avoid interactions between these standpoints. Right? So you're right, this restricts expressiveness because we cannot really say, according to standpoint D1, in standpoint D2 something else holds. Right? So you do not have this introspection capabilities across standpoints. But then again, these standpoints are not intended to express knowledge, right? So what one community knows about another community knowing, but it's more about the semantic commitments of these communities, how they use a certain logical language. Right? So that's the idea.
Because in your example, it's not really only about language, right? It's a really kind of content disagreement. So you might think that you could check, like, hey, if this would just be an idea, so you could check when the integration of these two standpoints would cause a kind of contradiction, and then maybe do some counting, for example, maybe something is concluded in many more standpoints or whatever to have a form of global inference or something like this.
Yeah. So the comment was, in this example, the disagreement is not only about how language is used, but it's really also about content, where one standpoint concludes something and the other standpoint concludes the opposite. And so your proposal, if I get you right, was to count the number of instances where one holds versus where the other holds, something like this. Yeah, or I mean, this is certainly interesting. Yeah, and something that we can also continue discussing offline. But as I said, this was a deliberate design decision because it is known that for multimodal logics, as soon as you allow to nest these boxes non-trivially, you immediately go to p-space complexity. Right? And then additionally, having non-monotonicity would even increase complexity more. And so we wanted to, at this first step, keep it simple while at the same time covering these existing languages in a standpoint localized form. So that was our intention here. Okay, so if there are no further questions, I thank you all for attending this course, for staying until the end. Enjoy the rest of ESSAI, and then maybe see you around at the next conference.